So I'm here, and looks. At least I was going to say you all are here. Certainly, everybody in the room is in the room. I don't know who else is coming. But anyway, I wanted to say last time I forgot to say at the end of the period to put that 1 in for the weight. Remember, I was talking about recursively calling it. So the initial ray through the pixel, one of those n rays that we were averaging, I should have put parentheses comma 1, the weight at 1 at that initial weight, and then the weight gets keeping multiplied. So both methods that I talked about last time, the method by multiplying the weights, and when the actual contribution of the new radiance, all those factors got small, you made it 0. Whereas it really was non-zero, even though with the weights, you know, the contribution will be small. And the other way, just by let's see, what was the other way? I've got to look at my notes and remember what it was. At a finite level of recursion, up to, say, 10 steps, you make it black. In both those cases, you're getting pixels that shouldn't be black that are actually contributing a black color. So this extra black color is being averaged in for all those pixels, and that means that you're biasing the final color that you're computing toward black. You're making it darker than it should be. And of course, depending on the geometry, some places will be darker than others. So even if you think of normalizing the picture so that the maximum brightness is 1 in any pixel or some other way, because your eye is really only sensitive to ratios, even the ratios will be wrong. And that means it'll converge to the wrong answer. So sort of statistical estimate, like a Monte Carlo estimate, is called unbiased. If you take enough samples using the method, you'll get closer and closer, you converge to the right answer. And, you know, since the mean of those samples is not really the integral we're trying to integrate because of neglecting those, you know, turning some of the samples black that shouldn't be, the answer is biased. So the other method I want to talk about is called Russian roulette. And it was actually invented in the simulation for nuclear weapons when they were trying to figure out how they did Monte Carlo estimation was actually used, I think, in the Manhattan Project to figure out what's happening physically when you're simulating a nuclear explosion. And basically, it's good for any kind of physical simulation, like this lights bouncing word simulation. In that case, it would probably be neutrons bouncing around, where it's hard to do the integrals analytically. And they had the same problem, when to stop bouncing their particles that they were simulating to find their effects. And so they decided to say, take some fraction. Let's just think about a half. Suppose at each bounce you decide with probability of half whether to continue or not. And otherwise, you just neglect, you know, that whatever that light energy or neutron energy, whatever it's going to be, is. Well, if you neglect the answer half the time, you know that your answer is going to be half as bright as it should be. So you just multiply the ones you do use by 2. So you get rid of, on the average, every other sample, but you magnify every sample you do get by multiplying it by 2. Then it will have the right answer, being unbiased, because you're compensating for the ones you're throwing away. So basically, does anybody know what the game of Russian roulette is? What is it? Yeah.
From the deer hunter, you take turns spinning a bullet in a chamber, and the players see if when they pull the trigger on them, they get the bullet or not.
Yeah, so it's a method of committing suicide randomly. So it's like this, you know, this photon is going to disappear or not. And so, let's see how to say that. Shall I modify my whole thing? I guess I'll do it the short way. I actually wrote complete notes in it, but well, I don't know. It's very similar. I'll just leave out a lot of the stuff. So we're going to revise this color path trace x and direction theta. And it's not going to have this extra parameter, either the count or the weight, but it is going to have a probability of reflection, p sub r. And in the book, that's 1 minus the absorption fraction. So absorption is when you think of the particle as not bouncing off the surface because it got absorbed by the surface. You know, every surface has a certain reflectivity, a probability that something that hits it is actually going to bounce. And if it's dark, it's going to have less probability. So, well, we're not doing something per surface. We're just making an arbitrary fraction. I said a half before. But say maybe you'd absorb 1/4 of them and 3/4 would be continued. Then you'd multiply the answer by 4/3. So what we're going to do is, actually, am I reading on the wrong page? Okay. So we're going to choose a random number. And u is going to be of uniform probability in the range between 0 and 1. And if u is less than this constant PR, which is the chance of reflection, they say less than 3/4. So 3/4 of the time you will continue to ray trace. Then we'll do what we did before. Trace array. Say x in the direction theta. So if it meets the scene, say I'll call a point y. In the book they call it y. Last time on the board I called it q. In a point y, the book didn't worry about if it misses because they're thinking of closed environments where I'm thinking of maybe you have objects floating in outer space and there's just, you know, some background color, or the sky. Maybe you're not modeling the hemisphere of the sky, you're just making a background blue. Then you want to pick a random direction. Psi with probability P of psi. And you'll let radiance, maybe I'll write it up here. This is the same formula I had the last time. Radiance equals LE of now it's the point y, to look more like in the book, going back in the direction minus theta, plus the reflected radiance. This is only going to contribute if it's a light source, FR of y, and this psi reflecting into the direction minus theta. And the other factors were cosine n at y and psi. And then the radiance at that point. And the radiance is what you'll do by recursively calling path trace at the point y in the new direction psi. But you have to divide it by the probability of psi. Right? Whenever you do a Monte Carlo estimate, you have to always divide by the probability so that it really gets the integral when you add them all up or average them. But now we have some else's. So here is the case if it doesn't miss the scene, something I didn't do in the background radiance is the background color. So far this should be, except for perhaps a change in notation, exactly what I had on the other time. And then we have, that's the end of this if. And now we have the end of this if. Let's see. This is the end of this if, and now the end of the other if is else radiance equals 0. Right? If we fail in the Russian roulette, and that 1/4 of the time happened because p maybe was 0.8 and this was 0.75, then we're going to contribute 0. Okay, and now what we have to do is return the radiance divided by the probability, which in the book they say 1 minus absorption. And the reason for that is we only took like 3/4 of the time, so we have to multiply it by 4/3 to compensate, which is effectively dividing by that probability. So that's the other way to modify the code I had last time, and now it's unbiased. Because we're compensating, we know instead of being 0 after a finite level of recursion, which we couldn't know in advance how many levels we'd actually need, or we can't compensate the other methods because we actually don't know how often they're going to hit black. But this one, we know what percentage it is that's going to hit black because it's by a probability rather than by what geometrically happens. And so we can compensate by, since we contributed probability times the radiance by only adding anything that fraction of the time, we can just compensate right here. So, and then this is done recursively. So on the average, how many recursive calls would you need? Well, there's always the first one inside that main loop where per pixel you're starting your path tracing, maybe multiple samples per pixel. I should point out, the way the book writes it, they're also choosing multiple samples within this loop. Right? So if you took, say, 10 samples for the first bounce, and each of those you needed 10 samples for the second bounce, and each of those you need 10 samples for the third bounce, your tree of bounces is going to grow exponentially. So your probability has got to be, I guess, in order for it to make it converge to a finite number, your probability has actually got to be less than 1 over n. But the way I'm writing it, I'm just saying only one ray. And this is the philosophy in Jim Kajia's original paper. Instead of using like multiple shadow rays to multiple light sources, we'll talk about, and I'll probably follow the book's way for that, you could pick a light source randomly and only sample that one light source. And in another pixel, you pick another light source randomly. So you're trying to, by the path tracing usually refers to what Jim Kadia did in his paper, where he always tried to pick only one thing to continue recursing. But you could do it with n. You just have to make the probability small enough to still make it converge. The formula would be similar. But now, in the second bounce, you're only going to continue bouncing with probability p sub r. I guess this looks like pr instead of p sub r. It doesn't matter. And of each of those bounces, the third bounce, I mean, this is how many times you have one. This is the first call recursion. We want the expected value of the number of calls. So there's always this call, and with this probability, there's one more call. And then with this probability squared, there's two more calls. And then if you've got two, with probability PR, you actually have a third. So this is the probability that you'll have three calls. When you add up the expectation of the first call plus the expectation of second calls plus the expectation of third calls and so forth, you're going to end up with the expected number of total calls to this routine per initial subpixel sampling ray. And what does this add up to? Remember your geometric series? Everybody's saying it's smaller. It's the first term, which is, for an infinite series, it's the first term divided by 1 minus the ratio. Right? So if the probability is a half, your expected number of calls is only 2. But yet, you could have arbitrarily many calls. And since those high number of calls are weighted by bigger numbers, like if you had 2 bounces, you'd be weighting by 4, and so forth in that case. You know, your expected answer when you call this, even though your expected computation time per ray is small, it could be large in certain rays, and so the answer is going to converge to the right answer if you have enough rays and wait long enough. So in that sense, this Monte Carlo method is unbiased. Okay, so now let me talk about direct illumination. So this is expected number of calls per ray. Basically, if you had an n here, you had n rays, each with this probability, and here, for each of those on the second bounce, it's like that. And so in order for this to work, this number, for this to converge, this product would have to be less than 1. So, you know, why bother with n if on the average you're going to have less than 1 anyway? Okay, so now direct illumination. So several lectures ago, I remember separating the illumination into a direct component and an indirect component, where it used the separation of L into LE plus L reflected. And that means if you want to estimate the radiance at some sample, you can have one method of estimating the radiance coming directly from the light source. I guess I have them here. This one, we could use one method of sampling light sources and another method of sampling, say, the BRDF or something. We'll talk about that probably next time. And then just add them up. And so to estimate the contribution of LE to the radiance L x theta. That means we have to, here is x, and here is theta. And by the direct radiance, what we're really trying to estimate is this hits some other surface here at y, and we want to sample the light source. Say here's a light bulb or something with a filament and a frosted light bulb or whatever. And we want to, instead of tracing random rays from y, as I've sort of done in this recursive call with random psi, we want to trace rays psi that selectively aim toward where we know the light sources are. Have I done that right? No, I've drawn my picture wrong. I'm thinking of a double indirect. I think what we're trying to estimate is x leaving in direction theta, and it's this direction psi that we're trying to make hit the light bulb. So you can, I was doing the like I did last time, the double thing. But I really only need one. We're trying to estimate the radiance that leaves x from illumination of light sources. And so what we can say is L direct is the integral over a hemisphere of LE, only the LE term, coming from x in direction psi, times the bidirectional reflection times the cosine term d omega. And we change that to integral over all the areas of the scene. So instead of putting L, I'm just putting this LE term because I only want the direct illumination. And if you do it in terms of areas of the scene, it's LE at some point Y going in direction, I guess it's XY, because that's the psi. Let's see. No, it's headed in direction minus psi at this point. It's headed toward X. So that's the vector from Y to X. That's the direction it's headed, right? So this psi is being sampled instead by sampling area on the areas of all surfaces. This is a conversion I made a while ago. And here is the bidirectional reflection at X for these two angles, but I guess now it's XY, which is the opposite of this, which is the psi, and this is the minus psi. And then we had the geometric XY that we needed to convert this d omega psi into a dA on the surface Y. And then we also had the visibility between X and Y. And so this has got this cosine in it plus the conversion of the solid angle to integration over areas. So we could sample over all areas in the scene. In fact, that's one thing the book proposes for direct illumination as a possibility. But it's wasteful because what we really know is only certain areas actually are glowing. You know, the sun is glowing, these lights are glowing, and the rest is just reflecting indirect light, and that we'll estimate separately maybe next time. So we're only trying to estimate this glowing thing, and only a subset of the surfaces are glowing. And so by sampling somehow over those subsets, we can concentrate the directions of the rays. And when we do the Monte Carlo estimate, you know, the probabilities will be adjusted so that we're integrating over and only over those light sources. We're not going to sample points on the whole ceiling, only on the pieces of ceiling that actually have lighting fixtures on them. And so that means we'll get the direct illumination for fewer samples because we won't waste samples that hit a surface for which L sub B is 0. So how can we do that? One way is to think of summing over the light sources. Say you have n ceiling fixtures here. Looks like we've got 12 in this room. No, we've got a bunch more near the blackboard. 6 more, 18. So we could have a sum over 18 integrals over the integral of the area. I think in the book they call this K. Area sub K of these terms. And this is the kth light source. Okay, so you could do this. Say we had a rectangular lighting fixture here. We could do it by jittered sampling if we want it. Or we pick a random point on the area. So if we pick a random point, then if this area of this light source is A of K, and we pick a uniform probability, then the probability of any given point is 1 over the area. Maybe I should put absolute value to represent the actual area of this region. Right? So if you have a smaller region, then per pixel there's a higher probability. I mean, per point on it, to make it integrate out to 1. So let's see. I think I wrote down a way to estimate this integral here. The problem is if we compute this sum, we're not using the principle of doing only one shadow ray that I mentioned before. So it's to not make the path tracing sort of trees grow exponentially. So suppose we only wanted one sample. Then we have to have a probability distribution for which light source we're going to pick. Right? Some random number that's going to get me one of these 18 light sources on the ceiling here. So assign a probability P of k to each light source. And then we can use the cumulative distribution function of those discrete probabilities, right? We only have a discrete number, n or 18 in my case, of events. We can assign them each a probability. And it doesn't matter how we do it. We might want to make that probability proportional to the total area of the light source or proportional to the total flux of the light source, which is area times the excident flux that's leaving per unit area to get the total flux that's leaving, because bright sources are more important or large sources are more important, or actually the product of size and brightness is the total flux leaving. But anyway, we have some method of choosing them. And because we're also going to divide by this probability of choosing that light source, by this general principle, we always divide by the probability, whatever our choice is, the choice will basically be canceled out, and we'll get an unbiased estimate of the integral. So maybe I'll write a kind of a direct illumination code here. So I guess I can keep this much. So we'll call it direct illumination. I shouldn't have tried to leave this here. So it's going to do the same thing. What we're going to do is select a light source k with probability p of k. Right? And we're going to use this cumulative distribution function of our finite collection of probabilities to do that. That's the very first way I showed you the cumulative distribution function without integrals. It was just a bunch of steps. So we're going to use a random number to do this. So I could say using a random 0 less than or equal to u less than 1 and cumulative distribution function of p of k. And then select a point on a k and a point, well, let me call it y. Probability. Probably what I should really say is the probability of y given k. Right? Because once we specify the light source, then we have a specific probability distribution on that light source. Like the one for these rectangle diffusers might be different than the ones for these long thin. They're also rectangles, but they're a different shape. Right? So for each shape, I have a different way of choosing my samples and maybe a different area. So the probability density depends on my first choice. And that's like when I talked about conditional distributions last time. So that's the notation for that. And then take the radiance equals LE at that position y going in the direction from y to x plus the FR, whatever terms I had there. in full detail, x minus theta going to the direction psi, which was what? xy? No, yx. Let's see. xy, right. That's the direction that the light's coming in from when viewing y from x times, I'm not going to write them all down. gxy is that thing with a bunch of cosines and 1 over the distance squared. And visibility, you have to determine by ray tracing. Trace ray from x to y, because y is chosen randomly on the light source, and this visibility factor might be 0. That's what's going to give you the shadow penumbra from the direct illumination. When that particular point on the light source isn't visible because something else is in the way, this will be determined by a ray tracing computation that you need to compute this. And then we have to divide by the probability of getting that point y, which is the product of two possible probabilities. First, the probability of choosing k, and then, and this book missed this multiplication sign, the probability of having chosen k, finding the point y, which is this conditional probability. So we're dividing by the product of those factors. And that's the fact, you multiply the probability of k times the probability, the conditional probability of getting y and k, and that's the probability of getting the two things k and y. Right? That's definition of actually conditional probability. And then just return the radians. I could have just said return the radians. Now, in the book, they do it a little differently. They start by saying radians equals 0, and then they do this thing n times. Some counter up to n. And then they divide by n. Right? So that is finding direct illumination by taking multiple samples. And if this was your final rendering where you were just doing one ray in the center of the pixel, like OpenGL does, but then wanted to get a Monte Carlo estimate for the shadow penumbra at that one ray, then you trace multiple rays and average them because you get less variance. But if we're already choosing multiple pixels, multiple subpixel samples for anti-aliasing and maybe depth of field and so forth, then I don't think we need this n here. I could talk about jittering, though. The jittering applies the same way. We could have a jittering rule that chose k, a different k, and a different subpixel sample for each choice of the subpixel sample. You know, you have this, we have a random permutation, but the random permutation would have to be among all light sources and all samples in the light source. So you take these jittered regions on each light source and, you know, add them all up to get the total number of squares on all of them. And then you could use jittering to pick which one. And if you did that, you should probably divide them so that each one has approximately the same area or approximately the same flux. So if you have a brighter but smaller, long, thin light source, you might want to make these closer together here to compensate for the fact that these are brighter than those per unit area. But you could still do jittered sampling just on the simplest thing to think of is a single area light source. Just like we made samples on the lens correspond to each subpixel sample, we can do that on the light source too. Okay, so what else do I want to say about this? Environment map illumination. So I am going to cover, I think in the syllabus that I printed the first time, I decided I hadn't included environmental illumination. But since now instead of missing, when we missed the class we fell behind, now we're ahead, I'm going to talk about that too. So the idea is of environmental illumination is usually you have a small object that you want to render as illuminated by an environment around it. So how do you capture that environment? If I just had a normal camera that wasn't a fisheye lens that could capture like a hemisphere worth, I would just take a lot of different pictures around the environment. And, they each have their own perspective and their own maybe barrel distortion of the lens or whatever that I'd have to compensate for. But I think there are already websites that do this, right? You can take a bunch of pictures and upload them to a website, and they'll, compensate for the perspective and any distortion in the camera and by matching the content to rotate and distort the images till they all match up and fill up the whole environment. The other way you can do it is, like I said, if you have a fisheye lens that can get a whole hemisphere, then you just have to aim it this way and aim it that way. And if your aim isn't exactly right, maybe you want to aim it 3 different directions. There are also these panning cameras that I've seen that they use for like big group photos where they can't open the lens. They don't have a wide enough lens, where it's sort of like a slit being exposed. As the camera rotates around the film, it's exposing, one slit each time it rotates, and it's actually building up this cylindrical panorama, which you can make go around completely around if you've got the right kind of camera. What else? Oh, the other way is you just take a very shiny sphere. And you just take a photograph, hopefully with a very long focal length, so that your viewing rays are almost orthogonal to the sphere, because the camera is way over on the other end of the wall. And here are these viewing rays, and they're hitting this sphere, and each viewing ray is reflecting off in a different direction. And viewing rays very close to the edge of the sphere are actually going to reflect off behind the sphere. And when you think about that, first of all, you can calculate that just by the way we've been calculating reflection vectors off the sphere, and you can figure out how the image of where these rays hit the image plane on this very deep telephoto lens correspond to directions from the center of the sphere. Basically, a single sphere will, get the whole set of possible directions if the directions really are at infinity. Because if the content is really at infinity, it doesn't matter whether you go from here or here. You should get the same answer. So theoretically, with just one of these globes, you can get the whole sphere at infinity. It's just going to be a lot of stuff really crowded at the edges. But with 2 or 3, you'll do better. First of all, the camera is actually in this image somewhere, and you might not want it in the environment, so you have to have another view that doesn't have the camera in it. And also, with more views, you can compensate for the fact that it's really crunched up at the edge. But that's a normal lens or a telephoto lens instead of a fisheye lens, which is probably much more expensive. But there's another problem with gathering data this way, and that is that if it's really an outdoor scene, you've got buildings and trees and stuff, but you've also got the sun. And even in this room, if I wanted your faces and also that very bright surface of the fluorescent tube that I can see up here, the contrast is too high. It's beyond the dynamic range of the camera. Because when you take an image with the camera, actually if it's a film camera, it's even worse than with a CCD, because it's got a curve where if this is actually the brightness of the image in terms of using that image, say, a transparency slide, it changes non-linearly. It has a toe here, and then a linear section, and then a shoulder here where it falls off when the film saturates. And these CCDs saturate too. They only have a finite amount of charge they can accumulate. And so what you need to do is you need to use several different exposure settings. Very dim exposures that will actually give you a true realistic value in the linear part of the exposure for what that fluorescent light or that sun actually is. And then very long exposure or wide lens or whatever it takes to get more flux in to get the shadows, like shadows under the tables here, or your dark clothes, or whatever. And then by combining those images, knowing the saturation characteristics of your film or your CCD, you can get one floating point value. And then you have what's called a high dynamic range image. And there are cameras that actually can do that for you. I guess they take a few images really quick and give you this high dynamic range, because that's really what you want for the illumination, right? If you want the illumination from the sky or the walls of this room, as well as the illumination from the sun and the lights, you want to know that you haven't saturated out the true energy of the sun like you would in a normal camera. Even your eye can't see the true energy of the lens because you're saturating the receptors in your retina. So suppose you do that. Then you have, for every direction, you can think of this sphere. Actually, the only part that's relevant is the hemisphere above your surface as a complete light source. So everything is a light source, and you just want to sample that sphere or that hemisphere. So we already talked about how to get cosine-weighted samples of a hemisphere. And you could just use that to sample this environment at infinity and compute, say, the lighting on each part of your surface. You could even do that just with one ray in the center of a pixel, and you get much more good illumination, but you wouldn't get shadows from the environment. So probably what you still want to do is you want to trace those rays through the environment to see if there are other objects casting shadows, nearby objects that aren't counted as the environment in infinity, that you don't think as actually contributing light. You wouldn't get the global illumination of the reflection off of them if you think, because you're only gathering this light at infinity. So now the question is, how could you sample that light weighted on the flux instead of weighted on the just by cosine? Well, actually, your weight is a product of three factors. I wonder if they're still on the board. There's the BRDF and the cosine and the light. And the more your sample, the more your probability distribution can approach the product of these three, I guess we're not doing this recursively anymore, right? We're assuming this is L environment, right? I'm saying this thing is represented by the environment map, which is function only of psi. The whole point of it doesn't depend on the position y, because you're assuming the y is really on a small object, and this environment in infinity is so far away that it doesn't matter what point on the object you go in that direction. The answer is the same. That's the philosophy there. So it's the product of these three factors, this one, this one, this one. Well, we talked last time about how you could sample glossy reflection, right? If it was Phong reflection. If you wanted to sample an environment map by the Phong reflection, we know the cumulative distribution analytically. And in fact, I suggested a couple times ago you could even pre-compute that. And then you just look it up as a function of the perfect mirror direction that this size will be distributed around. But suppose instead you had more of a diffuse BRDF, say it was constant. And you didn't want to worry so much about this thing. You wanted to sample proportional to this. Well, that's the same problem as, instead of just a sphere at infinity, it could be any light source that had unequal power per unit area. And one easy example of that is a stained glass window. We have light panes and dark panes. In fact, if you're doing it in RGB separately, some panes have more R and some panes have more G or B. And so you want to adaptively sample this textured light source. The environment is just a very wide-angle version of that. How can you do it so that your samples are proportional to the radiance in that direction, or on that position of the light source. Here it's direction, but it could also be a stained glass window here that had variable brightness, on each piece of stained glass. So what you want to do is, if you're given a function of either the texture coordinates here or, say, the phi and theta that represent your latitude and longitude on your environment sphere, how can you sample proportional to that? It's like a cumulative distribution, but that's a case where you need to sample, say, x first, and then for each x, you have to sample y. So the sampling in x, according to the cumulative distribution function of p sub x, the marginal distribution. So this px is going to be proportional to the integral from, say, 0 to height. Say this has width and height. Height of the radiance at x, y, dy. Right? You still have to normalize it by dividing by the total radius, so to make it integrate to 1. Right? Because if you integrate this all the way from 0 to w in x, that's going to give you the total flux. So if you put that in the denominator, it'll cancel. Okay, so this is a function of x because the y is integrated away, and that's the marginal distribution. So you're going to choose x proportional to the amount of light that's in that whole column. And then you have to sample y according proportional, why don't I say, to the probability of y given that specific value of x. Right? So that means if x is fixed now and y is varying, this thing integrates out to some number, namely this number. Right? When you divide it by this thing. And so that's the probability of those 2 points, which is what it's going to be proportional to the brightness. Well, why don't I say proportional to the brightness at xy divided by this, right, to make that integrate out to 1. And so basically what you have to pre-prepare is this cumulative distribution and a separate cumulative distribution for each column. And then you can first choose x to decide which column, and knowing which column you're choosing, you use the cumulative distribution function that you pre-computed for that column to choose y. So the examples in the book, it's this probability of x, y was really the product of the probability of some probability of x and some probability of y. It's like this dependence of the brightness was really like the product of 2 rows, in which case then it would be x and y could be chosen independently. But in the case where you have some bright spots in your environment, like the suns or these lights, you actually have to have a separate cumulative distribution for each. You can pick one variable to do first, and for each of those choices you have to pre-compute another one. Or compute it on the fly, but I guess that would take a lot of time because we're trying to estimate an integral. Anyway, that's what we're trying to avoid doing. But if you had a table, you have this texture table, you can add up the columns and do a cumulative distribution for each. And so you could do that either to sample a texture for its contribution to illumination, say from a stained glass window, or if you did it now our integral in phi and psi has that extra, I'm sorry, not phi and psi, it's phi and psi are the dihedral angles that a protein rotates around. And that's why I keep saying that, because I work on protein structure. Theta and phi are what we're talking about for spherical coordinates. You know, you have that extra sign theta in the integral, but you can do the same thing. I sort of hinted at it last time when they really were independent. But you can do the same thing when they're not and pre-compute the way to sample the environmental illumination. And then do that visibility to see if it's actually illuminating, and you get the sort of the shadows of the local objects that effect on the environmental illumination at infinity. Okay, so that's it for today.